yours. Please.
Okay. Thank you. How to remove presenter view? Here, yeah, okay. So can I start?
Yeah.
Okay. So my name is Desislava Petrova Antonova. I'm professor at Sofia University, St. Clement Ohridsky, and I'm also research group lead at Goethe Institute within the same organization. I'm going to present a paper titled Cognitive Impairment and Dementia Data Modeling, which is part of our research project devoted to building a digital twin of patients with cognitive disorders. So cognitive disorders can be a result of many medical conditions like single or repeated head injuries, infections, toxicity, and brain tumors. Most of them are caused by neurodegenerative disorders, vascular damage of the brain, and various combinations of them. The medical investigations related to diagnosis and treatment of cognitive diseases are characterized by a great variety of data, including medical imaging, neuropsychological, and neuropsychiatric assessment, cerebrospinal fluid biomarkers, blood tests, etc. The diversity of factors and indicators of cognitive disorders motivate us to develop a comprehensive data model which avoids incorrect data transformation and enables data integration from a variety of sources. The proposed data model keeps the semantic of the data in a human-readable format and accelerates the interoperability of clinical data sets. So here the concept of the patient digital twin is presented. It starts with creation of a patient data model by collecting data from a variety of sources. Next, seamless bidirectional connectivity is established between the physical patient and its digital twin. And data is ingested into a data storage and data pre-processing activities are performed, such as cleaning, consistency checking, linking, etc. On analyzed stage, different analytical models are developed using statistical methods, machine learning algorithms, and artificial intelligence as a whole. And the results are visualized as 3D views, dashboards, and other methods. Finally, the new knowledge obtained is applied to diagnosis and therapy of the physical patient, and the decisions lead to precise diagnosis and timely and adequate therapy. Here, the data modeling approach is presented. We started with definition of different requirements for the data model. Next, we built the data model following the process on the right. I will explain it later. And then we formalize data model using UML language and also YAML language, which is human readable and it's close to the natural language. And finally, we validate the data model using clinical experts. So here, the most important requirements to the data model are presented. They are divided into groups, domain-specific requirements and more technical. So the model should correspond to the functional specification of the patient record. It should be oriented toward presenting data at the patient level. The model should allow application for modeling all kinds of cognitive disorders in a unified way. It should integrate information through biomedical abstractions using proper medical terminology. It also should integrate diverse medical data at different level of granularity. It should have a temporal dimension related to historic data for the patient. It also should set correlations that discover a relationship between the patient's status, historical data, and disease progression. And the final domain requirement is that the model should be aligned with the external knowledge sources, such as ADNA database. This is open database with information about Alzheimer's disease. And regarding the technical aspects, the model should be written in appropriate format that is understandable by the medical experts, and that is why we use YAML language. And also it must provide a complete and non-contradictory structure to be used in the selection of the proper database and its creation. So it should allow usage of any kind of database to storage data. And here the main steps for modeling of the model are presented. First, we determine different groups of factors and indicators relevant to risk assessment, diagnosis of the disease, and its development. Next, we define factors and indicators along with their description. On the next steps, we distribute factors and indicators in different groups. And on the fourth step, we create a hierarchy of indicators. On the fifth steps, different dependencies and correlations are defined between factors and indicators. And finally, the model is optimized. Here, a UML diagram of the data model is presented. So we have four main entities: patient profile, medical history, clinical profile, and treatments. So I will explain now them. First, the patient profile includes information about the birth, gender, race, ethnicity, and native language of the patient. All these factors influence the disease and its progression. Next, anamnestic profile includes three main entities. This is social status, habits, and head trauma, if it exists. So the social status describes information about the education, also coexistence, financial status of the patient, employment, and other factors. The habits include smoking, drug abuse, alcohol consumption, also physical activity of the patient, sport, diet, and others. And finally, head trauma is described with the date of the event and with some images from computed tomography or brain scanning. And clinical profile include six main entities. First, imaging from MRI and computed tomography. Next, neuropsychological and neuropsychiatric assessment related to different cognitive domains of the patient. If there's some assessment of cerebrospinal fluid biomarkers, they are also included in the clinical profile. Also, there is entity related to the blood tests that measure the levels of vitamins, glucose, cholesterol, hemoglobin, creatinine, etc. And very important are comorbidities, such as arterial hypertension, obesity, atrial fibrillation, diabetes, and any other diseases. And the final entity is most likely dementia disease, which could be Alzheimer's disease, vascular dementia, mixed dementia, Lewy body dementia, frontotemporal dementia, also Parkinson dementia is here, and Parkinson plus syndrome. And the final entity is treatment profile, which described all medications prescribed to the patient, which are divided in 6 main groups presented here. These are medications for degenerative cognitive disorders, also those for cerebrovascular disease. The third group includes anti-platelet and anticoagulant drugs. Also, we have neuroleptic drugs, antidepressant drugs, and medications related to sleeping. So in summary, we propose a common, actionable, and shareable data model allowing researchers to conduct the research efficiency using available data sets for patients with cognitive disorders. Also, the model provides a native vocabulary which improves data availability, also saves efforts and standardized data to minimize the risk of rework and misunderstanding. And the model itself enables the application of machine learning and artificial intelligence algorithms by helping data scientists to understand the semantics of information through a holistic view of patient. And finally, it accelerates the interoperability of clinical data sets and supports content mapping by classifying and semantically annotating the data. And this brings me to the end of my presentation. Thank you for your attention.
Thank you. Let me check if we have the others. No, but I have questions.
Okay.
Your presentation is very interesting, mainly for me, because I had worked in the past, I had worked with music, how music can affect the minds of people, mainly the older people. For example, if someone listen on rock and roll, what feeling they have, or what's the difference between person A, B, or C, like that. I had worked with this some years ago. It's not my area now,
Yeah.
but I understand your research. My question is, do you have a real data or
Yeah,
you are
we
collecting
have.
in a hospital, something like that?
Yeah, we actually in Bulgaria we don't have data since a lot of data is used. So clinician keeps his own registry.
Very difficult.
Yeah, very
have
difficult.
Problems with consentments and clinical data. It's very complicated.
Yeah, that is why we started with Alzheimer's disease because their data open for research purposes, such as ADNA initiative, and looking for this data, and with the combination with the expertise from clinicians, we built this model. And the future steps are to create ontology and then to create a database, graph database on top of the ontology, which will facilitate the analysis.
But the final objective is help the doctors, the medical, or for example, recognize the patient's necessities to...
So the main goal is to translate the language from the clinicians to the language of researchers, because there are a lot of terms regarding these diseases, and they need to be understood first. And then if we, for example, build some machine learning or artificial intelligence methods, the researcher should properly select features to be included in the
that's
model.
the area that I work now, select and classifications and clustering the data. So I know that when I saw your presentation, I solved my research in the past, and now I'm the part of classification. It's very interesting for me. Oh, thank you very much. And I think it's only you in the section. Yeah, the author is not here. The online presentation is not here. Finished. Yeah. I know that I can close the window, but at the end I can close the window. But what should?
No, probably, okay, but probably.
Pena que diz que é o coisa.
Hello? Is anybody here? I am ready to present.
I am here, but I was waiting for the assistant, the technical assistant. I don't know who he is.
Okay.
Hello, can you hear
Hello?
me? I'm not the technical assistant of this room, but
Hmm?
the scheduling are delayed. Probably in a few minutes we'll start. Please keep in the section.
Okay. Connect.
Good afternoon to everyone. Session will be resumed in 5 minutes.
Okay.
Good afternoon to everyone, and welcome to Malaga to ICCSA conference. And now I'm Luigi, and I'm the chair session. And now I check if there is no problem with your microphone or your video. So can you switch on your video and your microphone, Dimitri?
Yes, I am here.
Okay, Ivan.
Yes, I'm here. Okay.
Okay. Diana, Pasquale, Ardelio, Giulio, Livia or Giovanni?
Okay, I'm here, Pasquale.
Okay. I see and I hear you. Okay. Navda? No. There's no. Okay. But okay, we can start with the session with the first presentation of Dmitry Nekulodov and Maxim Prostasov. I'm probably I say right, I don't know.
Yes.
Acoustic wave file simulation by the Ray method with approximation of a broadband signal propagation. The stage is yours. You can start, Dimitri.
Can you see my screen?
Yeah, can you move your slide only to check if it's all right? Okay. You can start.
Okay, thank you very much. So Many technical applications require calculating travel time and travel paths between known location of source and receiver. In seismic exploration, such problem, known as ray tracing, plays a significant role. Modern problems arising in seismic exploration are often three-dimensional, where the spatial size of the computational domain may be huge. So data processing techniques such as depth migration or seismic tomography should be computationally effective. It means that ray tracing subroutines, which are part of any seismic data processing packages, must be effective. Ray-based methods are usually used high-frequency approximation of seismic signal propagation. Classical ray method doesn't take into account the effects caused by the fact that spectra of the real seismic signals are band-limited. High-frequency approximation often leads to the non-physical behavior of rays and corresponding travel times. Here is an example of non-physical behavior of standard high-frequency rays in a complex model. As you can see, ray distribution are very chaotic, are very irregular. The limited spectrum signals propagate within some subvolume surrounding the ray. It is so-called Fresnel volume. Dominant frequency of the signal determines the width of this volume. Several approaches have been suggested during the past decades which address this problem. Of classical ray methods with varying degrees of efficiency. Each one has different advantages and disadvantages. The most common limitation is complexity of realization and sufficient computational cost. A promising approach has been proposed many years ago in this paper. It is simplified but very effective method to approximate the propagation of broadband seismic signals in complex environment. The key point of the Lomax method is that velocity is smoothed along the normal direction to the ray within a predefined range. The maximum distance from a central point is determined by the wavelength. It means by the frequency. For a given frequency, the average velocity is calculating as a weighted sum. It is shown here, where these values is values of actual model velocity taken at a certain point along the front. As a smoothing function, we use Gaussian function. However, other options are possible. So let the Lomax ray is constructed at some point. At this point, a unit tangent vector S is given. In the normal direction to this point, in some predefined distance L from a central point on the ray, we define two edges points on the front. At each of these 3 points, we calculate smooth velocity, like this. Central point movement determines new position of the central point, like this. The H point moves in the same direction respectively at the different distances, because velocity is different. Assuming that the front remains locally flat, from simple geometrical consideration, one can get an expression for the tangent vector in new location, in the next point on the ray. In the limit case, when this distance goes to 0 and time increment goes to 0, one can obtain a system of ordinary differential equation of Lomax ray. Lomax ray equations is very similar to the standard ray, but instead of actual model velocity in the point, here we must introduce smooth velocity. So they can think about this ray tracing method. We propagate not a wire, but we propagate beam. So here is some interesting consequence for this formulation. So actually we need to calculate different rate parameters, not along a ray, but at some regular grid. During standard ray tracing, travel times are calculated at the point in the model through which each ray is passed. In our application, we usually need to have these values determined on a regular grid. Using Lomax ray, it is possible to perform such interpolation in a very natural way. Let the Lomax ray is already given. Consider a point of the ray at time t. Then the ray moves from this point to the next point, t g plus 1. The flat wavefront passes through the area concentrated inside this trapezoid. The points on the regular grid may be located inside this trapezoid. Then such points are found, then travel times are interpolated in this point along the tangent direction, like it is shown on the slide. So, for our application, we need to calculate not only travel times, but also green functions of the, in this particular example, green function for acoustic wave equation. It just to remind it. Ray approximation of the green function for acoustic wave equation is given like this. Here we have travel time between 2 points, and here is amplitude factor. Its expression looks like this. Here we have interesting thing called geometrical spreading. We can calculate geometrical spreading factor approximately, like using finite difference. So we can calculate wave field with no use of very computationally expensive the dynamic ray tracing. So here is some numerical example. First, it is ray tracing. Sorry. Ray tracing through a solved body. Significant problem arises when the ray method is used to calculate travel times below solved bodies. Solved bodies may have a very complex shape. Seismic waves velocity in salt are much higher than in surrounding rocks. Usually it is problematic to construct rays passing through the salt body. Lomax ray can resolve this problem successfully. In this figure, we present a fragment of well-known 6B velocity model with a salt body of complex shape, which is shown in yellow. P-wave velocity in salt is 4.5 thousand meters per second. Meanwhile, in surrounding area, it doesn't exceed 3.5 thousand meters per second. Point source is located at the surface. We want to trace ray through the salt intrusion and calculate travel times on the horizontal line in the depths below salt in this line. Left figure shows standard ray. As one can see, ray distribution is very irregular. At sharp planar boundaries of the salt, the standard ray scatter. In the receiver line, there are areas where standard ray do not arrive at all. It is obvious contradiction with the real physical process of wave propagation. In the right figure, we show the Lomax ray calculated for the frequency of 5 Hz. As one can see, their behavior are much more physical. Lomax ray pass through the salt body and arrive to the receiver line quite regularly. So in this figure, we compare first arrival travel times. In the left figure, red circle Lomax ray travel times are superimposed on the synthetic seismogram, calculated using finite difference scheme for scalar wave equation. Blue circle corresponds to standard ray travel times. Red, as one can see, red circle perfectly fit the first arrival in the seismogram. This fact is shown more precisely in the right figure. The exact first arrival travel time picked from seismogram are shown in blue. Travel time according to the Lomax ray is shown in red. Travel time given by the standard rays are plotted as a black circle. The travel time residual between Lomax rays travel time and exact travel times does not exceed 4 milliseconds, which is fine for our purposes. Now we present an example of acoustic wave field simulation in the frequency domain. We compare ray-based results with the results provided by the finite difference method for acoustic wave equation. To simplify the comparison, we use a smoothed version of 6B velocity model. Figures on the slides show a fragment of the smoothed 6B model and the ray fields superimposed on it. Top figure shows standard ray distribution. Figure at the bottom shows the Lomax ray constructed for frequency 10 Hz. So in this slide and next two slides, we compare ray-based and finite difference results. Left figure shows that first arrival travel time tables calculated on the regular grid. Here results for finite difference simulation. In the right figure, we show a real part of the frequency domain wave field for a fixed frequency 10 Hz. Here we can see results obtained by standard finite difference simulation. Here we demonstrate that travel time calculated using the standard rate method after travel time interpolation on a regular grid. Here we can see corresponding 10 Hz wave field, which corresponds to this travel time table. In the left figure, we can observe holes at the edges of the computational domain, where no rays pass through these areas. As the number of rays in the area increase, the situation remains the same. The shadow zone doesn't disappear. Travel times provided by Lomax rays particularly coincide with the exact or finite difference first travel times. Residuals do not exceed 5 milliseconds. To compute these results, 10 times fewer Lomax rays were used than for standard ray tracing. The wave fields obtained using Lomax ray is consistent with the finite difference wave field. To prove this statement, I present this slide. In the slide, we compare vertical on the left and horizontal on the right, one dissection of the two-dimensional wave fields from the previous slide. Finite difference solution is shown in blue, Lomax ray wave fields are shown in red. Very satisfactory match is observed. Relative error with respect to finite difference modeling result does not exceed 4%. Here is my conclusion. Lomax method allows simple and efficient approximation of the broadband signal propagation. The comparative analysis of Lomax ray and standard rays in complex environment was performed. Results show the prospect of using Lomax ray in seismic exploration. Here is my acknowledgement. This is all.
Thank you, Dimitri. Thank you. If you stop your okay. So we can see. Okay. I see you better, no? If there's anyone who won't ask to Dimitri question.
Thank you.
No, thank you. Only a quick question from my point of view. No, in the last slide, you highlight that your method is, or this type of rays are good for seismic exploration. No.
Yes, I think so.
Yeah.
We expect.
Yeah, and so they can be a support to implement for the implementation of I don't know, seismic engineering. No. they can be a support
For sure.
in this.
It can be applied anywhere where rays are in use.
Okay, okay. So they can be a fruitful support for these files. So thank you, Dimitri, and
Thank you very much.
good afternoon. Thank you. And now we move to the next presentation, presented by Pasquale. I'm right?
Okay, I'm here, but
Yeah, I don't know if you or
Ivan Gallo is the second.
Sorry? Yes.
no. Sorry, Ivan. Sorry,
No,
Ivan.
don't worry.
Sorry, Ivan. Sorry.
No problem.
Sorry, and then Pasquale, see you later.
Okay.
And now we move to the presentation of Ivan Gallo with the name Nonlinear Approximated Value Adjustments for Derivatives Under Multiple Risk Factors.
Yes.
And the stage is yours. You can start if you are ready.
Okay, and then now I show my screen. Okay. You see the slides?
Yeah, can you move the next? Okay.
Okay.
You can start, Ivan. The
Perfect.
stage is yours.
Okay, so in this work, we develop a numerical method to approximate the adjustment value of European contingent claim where the underlying price is correlated with stochastic default intensity of two parties of the market. And
sorry, Ivan.
Yes.
Sorry. If you can put the full screen mode is better.
Yes.
If you can. Okay. Move. Only check. Move your. Okay. You can continue. Thank you.
So, this adjusted value can be characterized as a solution of a backward stochastic differential equation, and it can be nonlinear if we show as close-out value the adjustment value itself. In a Markovian setting, this value is a deterministic function of state variable verified at two-dimensional nonlinear PD. Our goal is to discretize and to solve numerically PD as an efficient alternative method to Monte Carlo simulation. So before the financial crisis of 2007-2008, the contract value was determined by taking the conditional expectation of discount price, but without taking account any credit risk. So after this crisis, the contract price needed to include the effect of potential default, and a theory of value adjustment was developed and arose some problem. In fact, now the evaluation of those contracts become very complex, and there is a search for numerically efficient method to approximate those price. So now we see we marked model. So we consider a time interval 0 capital T that represent the contract lives. Let a complete probability space endowed with a filtration F that represent the market generated by R, capital S, and other possible stochastic factor, where R is the risk-free interest rate process and capital S is the risky asset, and it's driven by the stochastic differential equation, where sigma is a constant that represents the volatility, and W is a Brownian motion. And finally, we assume to be in absence of arbitrage. In this context, we consider two parties, a counterparty, an investor, exchange some European claim with a payoff phi capital S capital T that represent the value of contract at maturity in the final time. And we suppose both parties may default at respective random time tau 1 and tau 2, where the generical tau I have this expression where the lambda are two f-adapted positive process and xi are two independent exponential random variable with mean 1. In general, those random time are not necessarily stopping time with respect to the filtration F. So means to price the defaultable contract, we need to extend our filtration F in a new filtration G, and we set this new filtration F union capital H1, capital H2, where the generical capital HI is a smaller filtration make it tau i's stopping times. Then we denote with the capital V bar the price of the defaultable claim, subject also liquid, funding, and collateralization risk. And a new filtration G, the price can be represented as a solution of a backward stochastic differential equation, where this first term, this first expectation, is the cash flow due to contract. Next, we have the cash flow due to collateralization account and the funding account, respectively. And this next term is cash flow due to hedging account, the hedging strategy. And in the last term, it's a partial recovery. And we will see it's a non-linear or linear, depend of shows this value, this epsilon, is named the closeout. In fact, in the next table, we see the general term with hypothesis. And in general, some terms are predefined in the contract, and other terms depend on evolution of the price. At time of default of a third party, we have the epsilon closeout value. It's called closeout value, is a recovery contractually agreed to be computed with a reference on price. And if we show as a closeout a portion of default free, we get a solvable linear BSD. Otherwise, if we take as a closeout value a fraction of defaultable price itself, we get a non-linear BSD not explicitly solvable, and we will study this second case. In this picture, the default time are not market observables, so the previous expression, the previous equation, must be projected on market filtration F. And for this, we use any result, any theorem and the key lemma, where the key lemma say for each G-adapt process exists a F-adapt process V, such that these two processes are equal on same set. It's important that this on same set T less of tau. In this way, we rewrite the previous equation in filtration F, and substitution the value the fraction of the defaultable value, we obtain this expression. In fact, we have the positive and negative part of V, where in this case we are not repeating the bar because the notation more simple. So in this case, we use the fraction of defaultable price, and we have the positive and negative part of V. In general, to approximation of this equation, the most widespread method is Monte Carlo simulation. But when we consider a triple stochastic process, they have very long computational time. Therefore, we look for alternative methods. For the stochastic intensity of lambda 1 and lambda 2, models by Sear process, and thanks to the failure condition, it guarantees the positive of the intensity. Then we assume the capital S, it's called underline, and intensity are correlated, and we denote with rho 1 and rho 2 this correlation. And B1, B2, and B3 are independent Brownian motions. So in this way, so we know under appropriate condition, the previous equation has a unique adapt solution V zeta, where zeta is a square integrable F-adapt process. Now we simplified our equation, so we assume there are the dividends, means P equal to 0, assume the rate R, F, C, and H are bounded deterministic function on time, assume the collateral account is a portion of the defaultable price, and finally the hedging function, capital H, is included in the dynamics if we assume a delta hedging of product. So in this way, under Markov assumption, we can write the default process as deterministic function in state variable, time underline and show intensity, and apply the ethos formula, we make sure that U verify the nonlinear PD, where the operator L is operator that include the partial derivative, first, second, and mixed partial derivative, and then we see the positive and negative part with the final condition U capital T xi zeta equal phi x. It's named the payoff. So now we want to result this PD, and we use the so-called method of line, that thanks to this method we approximate the spatial partial derivative by finite difference, and we get a ODE system that we result with a method in time integration, for example, Eulero scheme. In our configuration, we have an unbounded domain, so we can restrict, we must restrict our domain a rectangle, and we shows appropriate boundary condition. And we shows to exploit the Black-Scholes price function of phi with adjustment rate to include the default intensity. So we set the boundary condition, and then we expand space intervals and apply the finite difference. And for each grid point, xk, I, zeta j, the solution u, k, I, j verify the following ODE, where dl is a discretization of operator L in the previous PD. And in metric form, we have the order configuration in equation 6, where u evaluating t prime, u evaluating t, and e in x, e, zeta are three-dimensional tensor respectively, and x, e, zeta are vector in R, m plus 1. So now we want to result this system, and we use the Eulero scheme with capital N time sub-intervals of uniform length step delta t. So we denote the resulting of pitch-way approximation u evaluate in t x I zeta as u k I j evaluate in t for each x I zeta and respectively sub-interval for each e zeta k. And then now we want to present some numerical method of our numerical result of our method, take to Monte Carlo simulation as a benchmark. But in literature we cannot find the work to covering the general case. So we take a European collocation, a 6-month maturity, and for the parameter we set the same parameter in the Brigo et al. Papers. It is a report call, so the payoff is x less k positive part. And for C process, we see this. We set this value. Shows a property domain for H space, and we consider the case the independent of intensity and underline. So set rho 1 and rho 2 equal to 0. And in this table, we see with the Monte Carlo simulation, we get a value of 16.4391 in about 1 hour. While with our method of line, we get with 13 nodes for each space interval, we get a result close to the benchmark in less than a second. In fact, we get 16.44 in 0.60 seconds. And if we want to stabilize the first 2 decimal digits, we increase the nodes, the spatial node to 100, and we get a very reasonable computational time. In fact, we get a result in 46 seconds. Then, if you want to achieve a better accuracy, one maybe increase the number of spatial and also time nodes, inevitable pay attribute in terms of machine time. Then we see in this second table what's happened when introduction to randomness. For this, we consider different maturity, 6 months, 9 months, and 1 year, and compare the result with constant intensity. So means we study when the intensity are deterministic case, So the intensity are constant, and our case, the intensity are stochastic. And we see when increase the maturity, the randomness influence up the first decimal digit. It's confirmed it may be significant to consider stochastic intensity model for the long maturities. In conclusion, the advantage of this method is a simple approximation method, and we get short result in a reasonable computational time, and we have also quite good accuracy, and also we get a numerical convergence. But the drawback is we don't have the Markovianity. We cannot express the price process in the deterministic case, and we cannot use this method. And a big problem is if we increase the dimension of a problem, increase also the computational time. And for further work, we want to study the theoretical convergence and the error estimate, and we see what's happening when we introduce other stochastic factor. And I conclude. Thanks for attention.
Thank you, Ivan. Thank you. Are there any questions for Ivan? If there are no,
Okay.
I suggest a question from my point of view. Only a question, quick and simple. What are, if you talk in the last slide that about the other stochastic factors, no?
Yes.
What have you ever considered someone? No, so I don't know.
Yes, in the future, we think to consider, for example, the interest rate or volatility or the stochastic process. And when we include this other stochastic process, increase more the computational time of method of line. And it's not very fast. Then we want to study other method to include more stochastic factor.
Okay. Thank you, Ivan. Thank you.
Thank you.
And then we move to the next presentation of Pasquale.
Yes, I'm here.
Okay. So the next presentation is of Diana Conte, Pasquale De Luca, Ardelio Galletti, Giulio Giunta, Livia Marcellino, and Giovanni Pagano.
And
with the name,
there is another author.
Okay. And with
Patricia Paternos. Okay, now if can I start?
And the title is First Experience on Parallelizing Peer Method for Numerical Solution of a Vegetation Model. And your screen is clear. Can you move Okay, you can start.
Okay, thank you for presenting me. I am Pasquale De Luca from Partenipe University of Naples. I will present this work titled The First Experiences on Parallelizing Peer Methods for Numerical Solution of Vegetation Model. This work is joined with the different professors of University of Salerno and Partenipe University of Naples. Okay, now we start a brief outline which describes how the presentation will be discussed. In first section, we see an introduction, numerical background of related the problem that will be proposed. After we see the main core, the main contribute of this work, the parallel approach for solving in a good execution time this problem. And we close with the results and conclusion of the presentation. Okay. Vegetation patterns are ubiquitous feature of water-deprived ecosystem. On bare of ground, of small amounts of water are able to infiltrate into soil and the water run of course of water. In particular, we deal with the existence of a multitude of localized pattern of one species in otherwise uniform covered, and a second species also been observed as possible form of coexistence in a mathematical model. Here, we focus on a model of vegetation in semi-arid climatic zones and consider an example of principle self-organizing in ecology. So, we highlight the problem. Here we have the partial differential equation system with the initial conditions where U1, U2 refers respectively to trees and grass. W refers to the water. More in details, we have other constant variables considered for vegetation problem in third item shown in the slide that are no important in this moment because it can be generated randomly in a specific range values. So, aims of this work, we focus on vegetation problems, but we consider the partial differential equation system which governs the consider the problem. After we go to spatial and time discretization schema by converting the PDS to ODS system, after we highlight the numerical model for solving the previous ODS system, at the end we design a sequential algorithm based on previous numerical schema by closing with an accelerated version of the algorithm for achieving the best performance in execution times. So we use for the semi-discretization, spatial semi-discretization, the method of lines. And the first step is based on the method of line technique. Hence, we spatially semi-discretized the previous model by dividing the spatial interval shown in the slide into m-1 subintervals using a second-order central finite differences to approximate the involved derivatives. So the PDA system turned out to be an ordinary differential equation system where f1, f2, and f3 are row vector with the evaluation of the specific function on data that we see after. Second step of spatial semi-discretization is defined by generating a tridiagonal triplets matrix LDIF. In particular, we assume that U1, U2, and W are B0 outside their domain, and it turned out to be LDIF matrix. While by using periodic boundary condition, the matrix LDIF must actually be slightly modified, setting 1 on boundaries of a matrix or LDIF. Finally, by further compacting semi-discrete ODS system as shown, we achieve the equation numbered 4. After we go present the peer methods details. Peer methods are a class of two-step numerical schemas that solve a first-order ODS system. That we choose to highlight this, we consider as stage two-step peer method with a fixed step size h, shown in the equation 8, where we have the advancing solution yn is computed by approximating y on a specific time step. For example, in the last stage, computes the numerical solution at the grid points. Coefficient of the matrix A and B are characterized by the peer method used. So we notice that therefore that all stages are time dependent in a specific interval and are function of all the stages in the interval of previous time interval only, which are totally known and the current step time. Then, by denoting a class of capital F, the function evaluation of the stage at each discrete point Tn, and we have the final computational procedure shown in the expression numbered as 10, where n and ln are previous defined. So, previous schema generates the following pseudo algorithm, which summarizes the main computation operation. This algorithm shows the main operation needed to find the numerical solution of the previous problem based on discretization before. This algorithm has been first implemented in a sequential way. So in particular, the line we go to underline the time and space discretization on the line 1 and 4. Then to perform spatial semi-discretization in the line 5 and 6, we go to a procedure builds the diagonal matrix after the diagonal block matrix L is performed. So in the last lines, we apply the peer method that is mandatory to prime it, that is for time step n equal to 0, we need to pre-compute the values of y0 at all the stages. To this aim, in the algorithm, we use the explicit one step for the Runge-Kut that guarantees the peer methods maintains the same order of accuracy when computing the next value at the next stage. Finally, the last line illustrates the main computational core by solving several linear systems. And so we go here to propose the parallel approach because when we have large execution time by setting low time step for low step size for time discretization and spatial discretization, we have a very large data to analyze and manipulate. For this issue, we choose to parallelize the code by using CUDA environment, in particular the GPU machine. Our aim is achieve a gain of performance and balance the workloading to achieve better computational power to share among the GPU threads. Our GPU framework is based on CUDA kernels. In particular, we use QSolver and QBLAST for solving numerical algebraic operation. In addition, we use the dynamic parallelism approach in order to achieve best performance during the computation. So now we go advance by showing the GPU algorithm. Due to hypercomputational time required on finding solution propose the problem, we choose to show this GPU parallel code that aligns main features to be addressed to implement the numerical procedure in a GPU environment. That is, summarize the previous operation of the sequential algorithm. So we go to see in details some features, but in particular, I want to underline the aims and achieve a significant execution time, achieve a good accuracy level, and require small step size. So for priming the CUDA environment, we use these two routines in order to achieve large space on the memory management for loading large data. The first detail about our code, GPU code, refers to the space and time discretization by defining space and time grids by using a loop paralleling strategy, which refers to distribute among one thread the different operation of a one instruction. So in second line, we start the GPU parallel region. This instruction related to transfer data from host, from CPU to GPU and vice versa. The procedures are carried out only during the starting and final phase on the GPU parallel code because in order to improve the software performance, the overall computation is computed on GPU. Line 3 refers here to the spatial semi-discretization operation because a specific CUDA kernel has been designed for building the LDF matrix and after the L matrix in parallel way. We use the structural properties of the matrix L in order to perform a workload balancing among the domain problem and the threads number. In other words, we set the thread numbers uppercase T equal to dimension M of each thread computed the part of L matrix by performing operation concurrently. This step is implemented by using dynamic parallelism, which characterizes the CUDA environment and allows us to design the nested strategy of a parallel of a dynamic parallelism. Second explanation refers to the solution computation. In this step, a kind of nested parallelism is adopted. More specifically, each thread computes concurrently Y solution, final Y solution, by means the Runge-Kutta-4 method for priming the solution, which in turn has been implemented parallelized by distributing basic linear algebra operation among further threads. From line 5 to 7, at each time step and similar in previous step, a nested kind of parallelism is used for solving the basic linear algebra operation. Also in this step, we need to implement 3 specific CUDA kernels in order to perform evaluation of a linear or non-linear terms shown in a previous generical numerical schema. So at the end, we go to perform the solution, and in last line and 8, we close the GPU parallel region and transfer the data from GPU to CPU. We analyze some result by showing the architecture, and precisely we go to investigate the execution time required by varying the input size problem, and we find the best CUDA configuration for achieve best execution time by showing an execution time comparison among CPU and GPU. So In this slide, we show an execution time comparison by sequential and parallel implementation for solving the previous problem. The test is conducted by varying the input size problem and fixing the spatial grid very large. A standard GPU CUDA computation provides to preliminary set grid threads, and so we highlight the block and for threads grid is shown in the slide that give the best performance. First column table refers to sequential implementation which runs on a single core machine. Last column exhibits the GPU time. So we observe a significant gain of performance with respect to serial version. The time of a sequential version grows considerably when n increase. However, noticeable speed up is observed by CPU accelerated version. In detail, due to resource hardware limit on CPU, the tests are stopped to last two rows of the table about the n dimension because there is not enough memory layer for load data. So on the GPU is possible this one. This means that a file analysis in accuracy and efficiency terms can be done. So we closed the presentation. In this work, we presented a parallel strategy and related implementation for a problem in vegetation model by underlining a numerical procedure for discretize the time and space related to the problem. At the end, we have confirmed the gain of performance achieved from our parallel implementation by a specific comparison between two specific implementation. Thank you for attention.
Thank you, Pasquale. Thank you. Very interesting. But there are any questions? If there are no any question, I only a question for you. You used this method only on a semi-arid soil, or you have as a future perspective?
Yes, we have a future perspective
to use this method for other type of soils, no? Or for,
yes,
yes. For other for other climate condition.
Yes, in particular,
if you can, only if you can. Sorry, Pasquale. If you stop share screen, yes, I can see you.
Okay. I don't know if.
Okay. Now I see you. Now I see you.
Yes, in particular, thank you for the question because this is the first experiences that we have tried to parallelize the method, and we have chosen to apply this method to a vegetation problem such as the semi-arid problem. My PhD program refers to environmental data based on numerical analysis sector. So in the future, we have the idea to apply this method to other condition, climatic condition and semi-arid condition in other environmental.
Probably like Mediterranean yes. areas, no? Like yes. Italy.
For the problem, for current problem of water.
Yeah. It's really a current issue, a terrible current issue. So thank you, Pasquale.
Thank you very much.
Have a good afternoon. And then we move to Nauda. I write your name.
Yes, I'm here.
Yeah. Can you up your voice or your microphone because?
Okay. Yes, I'm trying.
Okay. The sound is better. Okay. The sound is better. Now it sounds better. And can you share your presentation so we can check if it's all right?
Okay. Yes. Can you see the screen?
Yeah. Can you move to the next slide?
Yeah.
Okay. So now that the stage is yours, you can start.
Thank you. I am Nauda Tarku from the Department of Mathematics, University of Mauritius. The title of my presentation is 6-order CV option valuation algorithm on non-uniform spatial grids. Financial derivatives are instruments whose values depend on or is derived from the value of another asset. Examples of financial derivatives are forward contracts, futures contracts, and options. An option gives the holder the right, but not the obligation, to buy or sell the underlying asset at a later date for a price agreed to in advance when the contract is first entered into. Option pricing requires a mathematical model with a correct specification of the stock price dynamics of the underlying asset. One of the most popular option pricing model is a Black-Scholes model with a log-normal diffusion process with a constant volatility given by the stochastic differential equation 1. The Black-Scholes model rapidly became the industry standard as the availability of closed-form solutions for European options made possible the dynamic hedging.
Navda, sorry. Can you click on hide button so we can see all your presentation? Because it is okay. Where there's stop sharing, no, next to stop sharing.
Stop share.
So we can see all your slides.
Can you
because
see
they are
it
cut by the bar, no?
wait. I share again.
Yeah. Sorry, but they are covered. The slides were covered by the bar.
Is it okay now?
Yeah. Okay. Perfect.
Okay.
Okay. Perfect. Sorry. Perfect.
Yeah. Can you see the full screen now? It's fine.
Yeah. It's very clear now.
Okay. Thank you. So yes, I was talking about the Black-Scholes model. The Black-Scholes model rapidly became the industry standard as availability of closed-form solutions for European options made possible the dynamic hedging of financial risk. However, with the appearance of strike and maturity-dependent volatility in market option prices, which is known as the implied volatility SMILE, after the 1987 market crash, the constant volatility Black-Scholes model was no longer adequate for hedging of options on a single asset with different strikes. The Black-Scholes model limitation led to the formulation of other models with better capabilities for fitting the SMILE and skew volatility structures. Extensions of the constant volatility log-normal diffusion model with better capabilities of fitting this market feature include stochastic volatility and germ diffusion models. However, such models lead to incomplete markets and therefore perfect replication is not possible. Under local volatility models, the constant volatility is replaced by maturity and strike-dependent volatility. These models have the advantage that they stay within the one-dimensional framework of the Black-Scholes model and thus lead to complete market models, which means that dynamic hedging portfolios can be constructed. One prototype is the constant elasticity of variance, CV diffusion, in which the volatility is a deterministic function of the asset price. The CV model nests several well-known models. When beta is equal to 1, the problem reduces to the
Now, sorry. Fernando Miranda say us that they are not shared the presentation. Someone has the same problem. Dimitri, Ivan, Pasquale.
No, I see all clear. I don't have a problem.
Okay, no, also me.
Okay, so it's all okay. Okay. So also Fernando said us that's all okay. Okay.
So
sorry. Can you continue?
Yeah. So the CV model nests several well-known models as special cases. When beta is equal to 1, the model reduces to the Black-Scholes model, while for beta is equal to half, we obtain the square root diffusion model. The CV process is consistent with two empirical market observations. The model incorporates the negative relationship between the asset price and its return volatility, and also it captures the volatility SMILE observed in market option prices. Empirical evidence show that the elasticity factor can be strongly negative in the index option markets. This is illustrated next. As beta varies from 0 to 1, the steep skew becomes flatter and becomes as flat as a Black-Scholes model as it tends to 1. The CV process is thus able to capture the volatility skew observed in market option prices. Closed-form solutions for European options under the CV model are in terms of the non-central chi-square distribution, whose computations become unstable when the volatility is low or when maturity is small, or when the elasticity parameter is close to 1. This is illustrated in the table. As we approach beta is equal to 1, rather than converging to the Black-Scholes price, the closed-form solution becomes unstable, while a simple finite difference method is shown to converge to the Black-Scholes price. It can be observed that the computational price is increased to about 290 seconds, while the finite difference method takes a maximum of 51 milliseconds only. This motivates the use of numerical approximation methods for the valuation of such options under the CV model. Let the time to maturity be denoted by 2, then the European put price can be obtained by solving the PDE4 with a given boundary and initial conditions. In this work, we propose high-order method for solving PDE4 on non-uniform grids. Numerical examples confirm 6-order convergence rate for options under the CV model. So we first localize the problem 4 to a finite computational domain due to the non-smooth payoff function for option pricing problems, which hampers the rate of convergence of high-order methods. A grid stretching strategy near the strike price is required to restore numerical solutions exhibiting high-order convergence rate. We therefore employ a grid stretching strategy to concentrate more grid nodes at the strike price, with the effect of decreasing the error at the point of discontinuity. Let M be the number of spatial grid nodes and S1 to Sm be the set of distinct non-uniform space grids. Let Y be the transform grid, then the non-uniform grid in S is constructed using 5, where Xi is a stretching parameter. Next, we let V denote the vector of option prices, and discretizing in space, it can be shown that PDE4 can be written in matrix vector notation as given by 6, where L is the matrix given by 7. The construction of the first and second order derivative matrices in 7 are explained next. Let the NP-dV denote the NP point approximation for the df derivative of V at the reference node Sm. Suppose that we require finite difference approximations dNP-dV. The derivatives of order NP-1 at a given reference node Sm can be written in the form of 8. Using Taylor series expansion about Sm, we have equation 9, where alpha m plus k is the displacement of any node Sm plus k to the reference node Sm. Truncating the Taylor series expansion up to order np-1 gives 10, and interchanging the summation, we obtain 11. For every d, we obtain np equations of the form of 12. Letting A be the Van der Waals matrix, we require the solution of 13 with the vectors W and B as defined on the slide, and the canonical delta is defined as in 14. Using Cramer's rule, we obtain the weights for a general NP point stencil as in 15. For instance, for an NP is equal to 3-point stencil approximation centered at the reference node Sm, we can obtain second-order approximate results, and we require the solution of 17 to obtain the weights. The weights for the first and second-order differential matrices are given in the table, and the differentiation matrices are given in slide 17. Similarly, the weights for a 5-point scheme is obtained by solving 19, which is expected to yield 4th-order convergence rate. And to obtain 6th-order approximations, we use an NP is equal to 7-point stencil approximation and the mathematical code which generates the NP point Van der Mon matrix, and the weights is given on slide 19. Once the semi-discrete scheme is obtained for the time stepping, we use an exponential time integration given by 20. The evaluation of the exponential matrix in 20 can be efficiently performed by the Karateodori-Feggia approximation and contour integrals. We now present some numerical examples for pricing options using the high-order non-uniform method. The first example prices a 1-year European put option when the stock price has an initial price S naught is equal to 100, when beta is equal to 1, which corresponds to the Black-Scholes model. It is observed that the expected convergence rates of order 2, 4, and 6 with the 3, 5, and 7-point stencil schemes are achieved respectively, while the 3-point and 5-point schemes yield a numerical solution having an error of magnitude 10 power negative 4 and 10 power negative 6 in around 22 milliseconds. The 7-point scheme leads to an error of magnitude 10 power negative 10 in only 22 milliseconds. The second example considers the pricing of a 1-year European put option where the stock price follows the CV dynamics with beta is equal to negative 2. It can be observed that the expected rate of convergence are obtained and the desired 6th-order results are obtained with a 7-point stencil. Also, highly accurate prices are obtained in little computational times. As mentioned earlier, it was empirically observed that beta can become highly negative, and this example illustrates that the method is highly accurate for different strike prices and highly negative betas up to, as you can see, -7. Finally, the last numerical example illustrates the effectiveness of the proposed method for pricing American options for which no simple closed-form formulas exist. Comparisons is carried out against the Han-Wu algorithm and in RBF-FD method. The results obtained using the 5-point scheme interpolated at the initial stock price of 100 are shown in the table. It is observed that the results obtained using the 5-point scheme agree well with the well-known benchmark prices which are available in the literature. So finally, to conclude, in this work, we proposed a new 6th-order method for pricing options under the stock price dynamics with heteroscedasticity, the capability to compute accurate prices for strongly negative elasticity parameters shows the merit of the new method. Thank you very much. If you have any question, I would be pleased to answer.
Thank you, Navda. Thank you. There are any questions for Navda? If there are no other questions, is my small question for you. You talk about American option or
Yes.
European market, no? But
Yeah.
you have you compared or have you implemented this method for other type of market, no? Or
Currently, I've investigated only European and American options, but this can be extended to, for example, barrier options or
okay.
any other path-dependent options.
Okay. So there are promising future perspective for your works in this way, no? Okay.
Extension to 2D also is in the pipeline.
Okay. Thank you, Navda. Thank you to everybody. And with your presentation, this session finished. And so have a good afternoon or have a good evening. And from Malaga, it's all. Bye.
Goodbye.
Bye.
Thanks. Goodbye, everybody. Goodbye.